Hello, in this video we're going to be talking about some of the essential information, tips, tricks, tools that you need to work with circuits. We're going to be talking about resistors connected in series and parallel and how to simplify them, some of the different meters that we use to take measurements when we're using circuits, and some equations for electrical power. So here we go. First thing, two words you will see a whole lot when we're dealing with circuits are series and parallel. These deal with different ways that we can make connections in an electrical circuit. So in series connection means basically connection in a line, connection in a series, so one then the next, then the next. And so you can think of this as the resistors are connected front to back. Let's take a look at this. One important thing to keep in mind is that whenever resistors or any pieces are connected in series in a circuit, the same current flows through because we have essentially one continuous loop. So here are two pictures. The one on the left is a circuit schematic. This is how we draw some of these things. And the one on the right is what this would look like physically on a breadboard. So these are three different resistors. They're connected front to back, I would say. So the connections are underneath the breadboard, like this way, this way, this way, and this way. So essentially I have a connection where I have my battery. This here is the circuit symbol for a battery or cell, where the long side represents plus and the short side represents minus. And so what we have is the positive terminal of a battery connected through a wire to one end of a resistor, which then is connected on the opposite end to the front of this resistor. The back of the resistor R2 is connected to the front of resistor R3, and the back of this is connected back to the battery. All right, so these show the same thing, and the idea here is that the current flowing through the circuit is the same everywhere because it's just one loop. There's nowhere for it to go. So if we're imagining our water flowing through pipes, the same amount of water is flowing throughout all the pipes all the time. It has to be because it's one continuous flow. So the current is the same, and this was what a series connection looks like. We also have a parallel connection. And parallel connection, you can kind of think they're connected front to front and back to back, or top to top and bottom to bottom, maybe. Here's what that looks like. So a parallel connection looks like this. The schematic would look like this, and what we can see is that with these wires, the tops of all of these resistors are connected. So this, and this, those 3 points are all connected by these wires, and by in the breadboard, these points, these holes are connected underneath this way. All right, so the top of this resistor is connected to the top of this resistor is connected to the top of this resistor, which are all connected to the positive terminal of the battery. So that's what this is showing us. This, and the top of the battery are all connected together by this wire. So they would all be at the same potential, if you like, and then they're connected at their bottoms. And so the bottoms are also all at the same potential. And so what that means is the potential difference across each of these is the same. So the drop across R1, R2, and R3 is the same as the drop across the battery. If that's a 9-volt battery, there's 9 volts across R1, R2, and R3. So the voltages are the same, but the currents are not, because the current can split. And if these resistors are different amounts of current will flow through them. Imagine every one of these is like a pipe junction. So there's some current flowing in that can some of it will divert that way, some will flow this way. At this junction now, some current's going to flow like that, some's going to flow like that. So there's different amounts of current, or you can picture amounts of water flowing through each of these resistors, but the voltage across them, the potential difference, is the same. All right, so that's the basic idea with series and parallel. Now, we can make some simplifications to our circuits when we're dealing with series and parallel connections, because if I have 3 resistors connected in series, I can simplify them and look at what we call equivalent resistances. So there's some rules for this that are in your data booklet. It depends on the connection, so you have to be able to identify whether you're looking at a series connection or a parallel connection, or sometimes combinations of both. All right, so let's look at the rules first. Here's our first rule. The series connection is really easy. If I have multiple resistors connected in series, they are equivalent to one resistor with a total resistance equal to the sum of their resistances. Okay, meaning if I have 3 resistors connected in series, this circuit is identical to another circuit with only one resistor whose total resistance is the sum of them all. So if I have 1, 2, if I have a 1 ohm resistor, a 2 ohm resistor, and a 3 ohm resistor all connected together, the circuit will behave in every meaningful way exactly the same as a circuit with a battery connected to a 6 ohm resistor. I'm doing 1 plus 2 plus 3. The total resistance is 6. So this circuit will like use the same amount of power, will generate the same current, will flow through it as this circuit. And math-wise, this circuit will be easier to deal with, depending on what we're looking at. All right, so oftentimes you're going to do problems like this where you're going to simplify down multiple combinations of resistors to a total resistance of the circuit is what we can calculate. What's the total resistance that the battery sees? Well, the battery sees 6 ohms of resistance. Doesn't matter to the battery whether it's connected to a single 6 ohm resistor or to a 1, 2, and 3 all connected front to back. Same exact thing to the battery is the idea. So we want to find the resistance of the circuit, or the total resistance, or the equivalent resistance. This is the rule we use for series. And there's another rule for parallel, which is more fun. Here it comes. When we connect resistors in parallel, the total resistance is defined by this equation. All right, so we're going to deal with fractions here. So 1 divided by the total resistance for a parallel connection is equal to 1 over the first resistance plus 1 over the second resistance plus so on, so on, so on. I could have 50 resistors connected in parallel, and I would do a fraction for every one, up to 1 over R50. All right, so when I have these 3 resistors here connected in parallel, the rule is 1 over R1 plus 1 over R2 plus 1 over R3 equals 1 over R total. And so we'll have to take one more step to solve for the total resistance. Don't forget about this step. The rule gives you 1 over R, so you need to flip your answer. All right, divide both sides by 1. Divide 1 by both sides, rather, to find the actual resistance. All right, let's look at an example of that to make sure you're feeling okay about fractions. But that's the rule. All right, both of these rules are in your data booklet. Okay, here's a very simple circuit, a parallel connection. I have 2 resistors. They're connected top to top and bottom to bottom. So this is a parallel connection. And so if I want to find the total equivalent resistance, I can use my rule for total resistance in parallel, which is the 1 over thing. All right, this is the American symbol for a resistor. You might see this from time to time. So just to be aware of it, of course, the IB will use this symbol for a resistor. Okay, if I want to find the total resistance, I'm going to use my data booklet equation. 1 over R total equals 1 over R1 plus 1 over R2. And I keep doing that for all the resistors in parallel. Here it's just 2. So I have 1 over 1,000. My first resistor is 1,000, as is my second. They're both 1 kilo ohm resistors. So of course that means 1,000 ohms. So 1 over the total resistance equals 1 over R1 plus 1 over R2. So I think I end up with 2 over 1,000. Okay, now this is the place where it's easy to like stop here and say, okay, so the answer is 2 over 1,000. Nope, that's 1 over total resistance. So 1 over R equals 2 over 1,000. So if I want to solve for total resistance, just flip both sides. I got 1,000 over 2. I got 500 ohms. That would be my total resistance for this circuit. So the battery sees an equivalent circuit would be the battery connected to a single 500 ohm resistor. To the battery, and in terms of the amount of power being used and things like this circuit is identical to this circuit, right? One thing you notice is that resistance decreases when you connect resistors in parallel. That is true. And the idea is you're giving the current more paths to flow through. So imagine if water's flowing, I add another pipe, well, more total water will be able to flow then. Right? I'm kind of, if I want to think about my resistance with the resistivity equation, I'm kind of sort of increasing the cross-sectional area, the amount of space that the charge has to flow through, if that helps. All right, but that equation will get you there every time. Let's look at a few other examples together. All right, you try this one, and you will have to take it in 2 steps. You first see if you can see it. If not, I'll give you a hint. So if you see what to do, go ahead and try it. All right, if not, your hint is these 2 resistors are connected in parallel. So simplify these 2 resistors first, and then you'll have a series connection. So this is multiple steps. So go ahead and give that a try. See if you can combine these resistors and then combine the total circuit and see what you get for total resistance. Okay, here is how you want to approach this. This is going to be a multi-step thing because it's not just series or just parallel. In fact, R1 is right now not connected to any single resistor in series or parallel, so I can't do anything with R1 yet. The connection I see is R2 and R3 are connected in parallel. They're connected at the tops, they're connected at the bottoms. And so that's a parallel connection, so I can simplify those. So what I'm going to do is create a kind of in-between circuit. We're not going to be done yet here, but I can simplify this one step by taking my two parallel resistors and finding their equivalent resistance, because then that whole thing will be connected to the 20 ohm series. All right, so this right here, 1 over the resistance here is going to be 1 over R1 plus 1 over R2. And so in this case, they're labeled R2 and R3, but I got to do 1 divided by that much resistance plus 1 divided by that much resistance to give me 1 divided by the total resistance of this whole section of the circuit. And so math, I got to do 1 over 10 twice. So 1 over R equals 2 over 10. Again, don't just say 0.2 because that's 1 over R. So the resistance of this section is 10 over 2, aka 5 ohms. All right, so the equivalent resistance here is 5 ohms. So I got 5 ohms here. And now, this is a nice easy circuit to simplify. I have a 20 ohm resistor connected to a 5 ohm resistor in series. The series that rule is the one that makes everybody happy because you just add them. And I get 25 ohms. 20 plus 5, that's it. In series, the total resistance is just the sum of each resistance. All right, so this circuit has an equivalent resistance of 25 ohms. That's how you would apply those rules. All right, one more to try. This one's fun and exciting. There are multiple steps you'll have to take to this, so take it one thing at a time. You go ahead, pause the video, and try this problem. Can you find the total equivalent resistance of this circuit? Okay, did you do it? Good job. Let's look at what you should get. First thing I want to do is simplify this section here. I have the only connection I can deal with off the bat is this parallel connection, 6 and 3 in parallel. So I'm going to do my fraction rule. 1 over the resistance here equals 1 over 6 plus 1 over 3. All right, I'm adding fractions, so 1 over 3 I could say is the same thing as 2 over 6, which gives me 1 over R is 3 over 6. In other words, if I solve for R, I get 6 over 3. That's 2 ohms. All right, so now we got something. I have up top a 3 ohm resistor connected down here to what I've simplified to be now a 2 ohm resistor connected to a 4 ohm resistor. The 2 ohms and 4 ohms. All right, now the next step that you want to see is that I do have one, and the rest of the circuit is out here. Just looking at this part. Okay, I have a series connection right here, and that's the next step I have to take. Nothing is simplified beyond that yet. So that's the next step I have to do and say the equivalent resistance of these two connected in series must be 6. That's 2 plus 4. So I can simplify a little further and say, okay, this is the same thing as having a 3 ohm resistor connected in parallel to a 6 ohm resistor. 2 plus 4 gives me that 6. So that's my series rule. And now my last step is that I've simplified it down to 2, and now I have 2 resistors in parallel, a 6 and a 3 in parallel. Hey, that's the same math we did right here. I'm going to get 1 over 6 plus 1 over 3 equals 1 over R. I do the same math, and I'm going to get the total resistance of this circuit is going to be 2 ohms. So that would be my answer for this one. 2 ohms. 2 ohms is the total. All right. So that's the process. You want to just look for whatever series and parallel connections you can find, simplify them down, and do this. When we start doing some math where we want to find the total resistance, when we're talking about electrical power, or any number of reasons, you might want to do these simplifications. All right, so that's how you use those equations in the data booklet to simplify these circuits and find equivalent resistances. Okay, another couple things that you want to know are what we call voltmeters and ammeters are 2 meters that we're going to use to take measurements in a circuit. Often, practically, we're actually taking these with the same device. It's called a multimeter because it can measure both voltage and current. So knowing how these work is really important because if you're using your multimeter, you need to make the corrections the right way. All right, you need to take voltage measurements in a certain way and you have to take current measurements in a different way. And if you mix them up, you will probably pop a fuse on the multimeter, and then I will give you a screwdriver and teach you how to fix it. Okay, but it is important that you make sure you know how to connect these things correctly, or else, number one, you'll break it, and number two, the values you get will not be correct. Okay, so here's the idea. Voltmeter does what it sounds like. It measures volts. It measures potential difference. So it's going to measure potential difference, which remember is we sometimes in slang call voltage, and across 2 points in a circuit. So I need to do a parallel connection. So when I connect a voltmeter, if I have a circuit, ignore the V for a second. I just have a circuit with a battery connected to a resistor, which will be connected through an LED. So this will light up a little LED. Resistor is here to control the current. If I didn't have the resistor here, the LED would probably pop, depending on how big my battery is. So maybe I care about what's the potential difference. What's the voltage across the resistor? If I have a 9-volt battery here, maybe the resistor is using up 6 volts or something. All right, so this is how you connect your voltmeter. It is connected in parallel. So I connect the top of the one side of the voltmeter to the left side of this resistor, the other side to the right side, and it'll tell me the potential difference between these 2 points. So the voltmeter kind of creates its own loop. The idea here is that it's kind of touching both sides to figure out the difference in energy, more or less, right? The difference in voltage between the two. We don't want any current to flow through the voltmeter, though, because we don't want it to influence our circuit in any way. We want it to be a totally impartial observer and just measure what's going on without changing the situation. If current flowed through the voltmeter, things would change. It would divert some current through the voltmeter. The LED would get dimmer. We don't want that to happen. So to get around that, the voltmeter has infinite resistance. An ideal voltmeter would have an infinite resistance. That's the rule for a voltmeter. Now, realistically, of course, there's no real infinities that we can seriously have in this case, which just has, like millions and millions of ohms of resistance. It's got a very, very high resistance. So much so that there's effectively infinite resistance and effectively no current will trickle through it. So it measures voltage without drawing any current, which is what we want for a voltmeter. All right, this is a memorized thing. It's very common on paper 1 or things like this for them to ask you about voltmeters and ammeters. How do you connect them and what are their resistances? So for a voltmeter, you connect it in parallel and it's got infinite resistance. That's the ideal voltmeter. Okay. The second type of meter we use, and the second way you use a multimeter, is to measure current. In this sense, we call it an ammeter. Think amps. Ampere is the measure of current. So an ammeter will measure current through any section of a circuit. In this case, I have a simple 1-loop circuit, so this will tell me how much current is flowing through. In this case, it is connected in series, and so when you use an actual multimeter, you need to break the circuit and then connect it through your ammeter. If you connect an ammeter in parallel, that's when you will pop a fuse, because it's designed for current to flow through it. That's the whole point. Current has to flow through it so that it can measure how much current is flowing. So it's connected in series. It's connected in the loop as part of the loop. So I would remove the connection between the LED and the battery and stick this meter in between. So the LED would connect to one side of the ammeter, and then the other side of the ammeter would connect back to the battery to complete the loop. Okay. Because the current is always the same everywhere throughout a loop, this thing will measure the total current flowing at every single point in the circuit. Again, imagine water flowing. The rate of the flow of water has to be the same everywhere. It does not slow down after it passes through the resistor or anything. Imagine this is all one big pipe full of water with a narrow section, and a section where it's like turning a wheel or something, and a section where there's a pump that's helping it to keep moving. Right? But so all of the water must be flowing at the same rate. It's not like there's sections of the pipe where there's no water and sections of the pipe where there's lots of water. It's all flowing at the same rate. So this will measure that rate, the current. And the idea here then is if current is flowing through the ammeter, I want it to have zero resistance. I don't want it to use up any energy. I don't want the charges moving through it to give off light or heat up the ammeter or anything like that. So it must have zero resistance, and then there will be zero voltage across it. That's all the stuff I want. All right, so the ammeter should have zero resistance. Current should pass through basically with the charges unaffected. And I can measure current then without affecting the circuit. Okay, so those are the things you want to memorize. Again, voltmeter has infinite resistance and is connected in parallel, and the ammeter has zero resistance and is connected in series. And last little bit, one other equation that you'll use a lot when analyzing circuits, it's really three equations combined. And it's equations for electrical power. These tell you about how much power is being used or dissipated or generated by something in a circuit. They are very contextual. So there's three different equations here, really. Power equals VI, or a lot of times you'll see power equals IV. And all they're doing here with the other parts of the equation is combining, doing some substitution with our other equation, V equals IR. These are our main two circuit equations then that we want to be thinking about when we're analyzing circuits. All right, so all they're doing is saying, okay, V equals IR. So for example, let's substitute IR in for V. Well, that gives us this equation. I times R times I means I squared R. Or let's substitute, let's see, what do we got? V over R for I. So if I multiply V by V over R, I get this third part. So it really just depends on what you're looking at, what you have. You know, if you don't know the resistance of something, you would use this version of the power equation. If you need power, if you don't know voltage, you'd use this equation. If you don't know current, you would use this equation. All right, so they all come from the same place, which is power equals I times V. That's kind of the most defining part of it. And it really just depends what you're interested in. If you want to know how much the rate at which heat is being dissipated by a resistor, for example, that kind of rate of energy transfer in watts, which of course joules per second, right? So how many joules of heat is this resistor shedding off every second? Maybe I use I squared R, where I multiply the current through the resistance squared by the resistance of the resistor. But if I want to know how much power is being put out by the battery, maybe I multiply the voltage of the battery by the current. That's probably the one I use because R, it kind of talks about a circuit component that's got a resistance, that's got a load. Okay, so it really depends on the context. What do you have? What do you need? But remember, it's all very contextual, right? Every single thing in your circuit's going to have a different voltage across it, probably, possibly, depending on the connections. Maybe there will be different currents in different parts of your circuit. So you need to think about what you're looking at, decide what you know about that section or element, whether it's the battery or a resistor or what, and then use the part that applies to you. All right, so this is one that will take some practice. You have to look at a couple of different situations and think about how to apply them. But always just ask yourself this question first. What power am I talking about? And for that section of the circuit, do I know anything about voltage, current, and resistance? That'll let you decide what equation to use if you're talking about power or energy, of course, or anything like that. Because, of course, last thing to remember is that power is work over time. So it's how energy changes with time. All right, so of course you can figure out how many joules of energy if you know something about the time too. All right, so there you go. Those are some of the most basic and fundamental equations we're going to need to analyze circuits in different contexts that you will be putting to use in the very near future. All right, so wrap your head around those and have fun.